The noise arrived before the machine did. Men standing 6 blocks away described it as a metallic thunderstorm rolling through the streets of Lower Manhattan. Windows rattled inside tenement apartments. Loose brick dust drifted from ceilings. Steam burst upward through iron grates in the pavement, while crowds gathered at construction fences just to watch the earth shake beneath them. Then, the hammer dropped. 14,000 tons of steel, pressure, cables, boilers, gears, and momentum came crashing downward into the skeleton of a new American city. For a fraction of a second, the entire structure beneath it screamed. Rivets exploded red-hot across the worksite like artillery fragments. Iron beams bent into alignment under forces no human body could survive. Workers balanced hundreds of feet above the street on narrow girders slick with rain, ash, and machine oil, while cranes swung overhead, carrying sections heavier than locomotives. And every minute the machine stopped, money vanished. By the early 20th century, American cities were no longer expanding outward. They were climbing upward into smoke-darkened skies. Banks wanted taller towers. Rail companies wanted denser terminals. Insurance firms wanted monuments of steel that could survive fire, wind, and time itself. But height created a terrifying new problem. Steel strong enough to hold a modern skyline could no longer be shaped by ordinary tools. The old methods were too weak, too slow, too human. So engineers built industrial giants powerful enough to bend the skeletons of cities into existence. They called these machines progress. The workers who stood beneath them often called them something else. Because across the rising skylines of America, the same question followed every new tower into the clouds. How many men could a city consume before it finally stood complete? Before the skyscraper became an American symbol, the city was a horizontal thing. It spread outward in brick, stone, timber, mud, and smoke. Streets stretched endlessly away from rivers and harbors, while buildings remained trapped close to the earth, rarely climbing higher than 6 or 7 stories before. Weight, fire risk, and structural weakness made further height impractical. Human civilization had built upward before. Medieval cathedrals rose over European towns. Ancient monuments climbed toward the heavens through forced labor and stone engineering. But commercial cities were different. They demanded density, speed, profit, and repetition. They were not built for symbolism alone. They were built to contain millions of people, endless paperwork, industrial finance, machinery, cargo, heat, and movement. By the middle of the 19th century, American cities were beginning to suffocate beneath their own success. New York became the clearest example. Immigration surged through its ports in staggering numbers. Factories multiplied along the waterfront. Railroads connected the Atlantic coast to industrial interiors thousands of miles away. Banks, insurers, shipping firms, and trading companies flooded Lower Manhattan searching for space that no longer existed. Land prices exploded. A single acre in the financial districts of New York or Chicago became worth more than entire rural towns. Businesses competed violently for proximity to ports, rail stations, and financial exchanges. Every square foot mattered, yet the city remained trapped inside construction methods inherited from older centuries. The problem was weight. Traditional masonry buildings relied on thick, load-bearing walls. The taller a building became, the thicker the lower walls had to grow in order to support the immense pressure above them. At moderate heights, this worked adequately. But beyond 10 or 12 stories, the walls became monstrous. Ground floor masonry sometimes reached 6 feet thick or more. Windows narrowed. Interior floor space disappeared beneath structural mass. The building effectively consumed itself trying to remain standing. And even then, catastrophe remained possible. Fires haunted 19th-century cities like permanent predators. Entire districts were built from timber floors, wooden roofs, coal-heated interiors, oil lamps, and primitive electrical systems. Firefighters struggled with low water pressure and inadequate equipment. Once flames entered dense urban neighborhoods, entire blocks could vanish overnight. The Great Chicago Fire of 1871 revealed the terrifying vulnerability of the industrial city. Flames consumed thousands of buildings, while smoke turned daylight into darkness. Brick cracked under heat, iron warped, streets filled with refugees carrying whatever possessions they could save before the firestorm overtook them. Insurance companies lost fortunes. Investors panicked. Urban planners faced a brutal reality. The future city could not survive using the construction logic of the past. But rebuilding demanded something stronger than brick alone. Steel emerged as the answer. Not decorative steel, structural steel. A new skeletal method began appearing in American architecture during the late 19th century. Instead of relying on massive masonry walls to carry weight, engineers developed steel frame systems where internal columns and beams supported the structure like the bones inside a living body. Walls became thinner curtains attached to the frame rather than the primary support system itself. The implications were revolutionary. Buildings could now climb higher without becoming impossibly heavy. Windows could expand. Interiors opened into larger office spaces. Elevators made upper floors commercially valuable for the first time in history. Suddenly, the sky itself became profitable real estate. But this new vision created another problem equally severe. Steel was unforgiving. Unlike wood, it did not yield easily to hand tools. Unlike stone, it demanded exact alignment under immense pressure. Every beam had to connect precisely with thousands of others inside a rapidly growing framework suspended above crowded city streets. A single error could destabilize entire sections of a building. And the higher these structures climbed, the more dangerous every correction became. At ground level, workers could still rely on familiar methods. Smaller iron components might be adjusted manually using hammers, wedges, chains, and portable forges. But skyscrapers required beams weighing several tons each. Rivet holes needed exact alignment across enormous distances. Columns distorted under temperature changes. Wind caused partially completed structures to sway. Nothing remained perfectly stable long enough for slow manual labor to keep pace with industrial deadlines. Construction itself became a race against physics. Financial pressure intensified the danger further. Every unfinished building represented trapped capital. Investors demanded speed. Railroads needed terminals completed immediately. Insurance firms expanded faster than existing offices could contain them. Newspapers celebrated height as a symbol of national power. American cities entered a competitive vertical frenzy where each new tower attempted to surpass the last. Steel production exploded to meet demand. Pittsburgh burned day and night beneath furnace smoke. Great Lakes shipping networks hauled iron ore in endless quantities. Rail systems transported coal, coke, limestone, and finished steel across industrial corridors stretching hundreds of miles. Entire regions reorganized themselves around the appetite of urban construction. Yet once the steel arrived at the city, another brutal challenge emerged. How could human beings physically shape such enormous material at such heights? The early skyscraper era was not clean engineering. It was violent improvisation. Workers known as roughnecks, connectors, and riveters balanced on exposed beams hundreds of feet above the streets with almost no safety equipment. They hauled steel into position using derricks, steam winches, ropes, hooks, and raw physical coordination. Riveting crews worked in terrifying synchronization. One worker heated rivets until they glowed white-hot inside portable furnaces. Another tossed them through the air using metal tongs. Catchers trapped them in buckets or bare gloves before inserting them into beam joints. Pneumatic hammers then slammed the rivets into place while sparks burst outward in showers. Every connection mattered. A failed rivet could weaken entire structural sections. Misaligned beams required enormous force to correct. Men used drift pins, pry bars, and chain systems to pull steel into alignment manually, often while suspended over open air. In winter, frozen metal became brittle and slippery. In summer, steel surfaces grew hot enough to burn exposed skin. Rain transformed narrow beams into lethal pathways coated in oil and soot. And beneath all of it remained the constant pressure of time. Construction schedules became increasingly impossible as buildings grew taller and more ambitious. Architects imagined towers never before attempted. Developers promised completion dates that ignored physical reality. Cities demanded rapid expansion to maintain economic dominance. Human labor alone could no longer satisfy the scale of industrial ambition rising across the American skyline. The machine had to evolve. Heavy forging presses already existed inside steel mills and railroad factories. Steam hammers had transformed industrial manufacturing during the 19th century by delivering massive controlled impacts impossible for manual labor. Hydraulic systems multiplied force through pressurized fluid. Giant cranes reshaped shipping and dock construction. Engineers began adapting these industrial principles directly to urban construction. The logic was simple and terrifying. If steel could not be forced into place by human strength, then the city itself would require machines powerful enough to overpower the material entirely. The new machines would not merely assist workers, they would dominate the construction environment around them. Massive pneumatic riveting systems appeared first. Steam-powered hoists followed. Hydraulic alignment tools expanded in scale. Temporary rail systems climbed unfinished buildings, carrying materials vertically through skeletal frameworks. Portable boilers fed networks of hoses and compressors that transformed construction sites into mechanized battlefields of heat, pressure, smoke, and noise. But the true transformation arrived when engineers combined industrial forging logic with skyscraper assembly. The gigantic structural machines emerging by the early 20th century were not singular devices. They were integrated systems of crushing force designed to bend urban steel into submission. Tower cranes, riveting engines, cable systems, compression hammers, lifting platforms, and hydraulic alignment rigs merged into coordinated industrial organisms weighing thousands of tons altogether. They became temporary mechanical cities inside the cities they were building. Workers entering these sites no longer operated in ordinary construction zones. They entered environments ruled by machine rhythm. Steam whistles dictated movement. Hammer strikes controlled communication. Boilers generated constant heat. Cable drums rotated endlessly. Steel groaned under pressure day and night. And every man understood the same reality immediately upon arrival. The machine did not stop for injury. It did not slow for exhaustion. It did not care whether the workers beneath it survived long enough to see the finished skyline. Because by then, American industry had accepted a brutal calculation. The city was worth more than the bodies required to build it. The steel colossus was not born from architectural ambition alone. It emerged from panic. By the 1880s, the United States was transforming faster than its infrastructure could endure. Railroads stitched together continents with astonishing speed. Oil fields multiplied fortunes overnight. Factories expanded across river valleys beneath permanent furnace smoke. Ports overflowed with cargo arriving from Europe, South America, and Asia. Immigration pushed millions into industrial cities already collapsing beneath overcrowding, disease, and economic violence. America had entered the age of vertical capitalism, and vertical capitalism demanded a new kind of machine. The turning point came after a convergence of disasters and opportunities reshaped industrial construction almost simultaneously. The Great Chicago Fire proved that older urban systems were structurally vulnerable. The invention and improvement of safe passenger elevators made upper floors commercially desirable. Most importantly, the Bessemer process and later open-hearth steel production dramatically reduced the cost of structural steel. For the first time in history, Immense quantities of steel could be manufactured rapidly enough to redefine entire cities. Pittsburgh became the furnace heart of this transformation. Andrew Carnegie's steel empire expanded through brutal efficiency and relentless consolidation. Blast furnaces burned continuously beside rivers blackened with industrial runoff. Rail lines delivered iron ore from Minnesota, while coal arrived from Appalachian mines, where workers labored under conditions barely distinguishable from captivity. Inside the mills, temperatures exceeded survivable limits near the furnaces. Molten steel moved through rolling mills in glowing rivers, while shift workers endured 12-hour rotations beneath smoke, thick enough to darken daylight. Yet these steel mills alone could not create skyscrapers. The real challenge waited hundreds of miles away in cities where land values climbed higher every year. Chicago became the first great laboratory. After the fire of 1871, reconstruction occurred at industrial speed. Architects and engineers experimented aggressively with steel framing systems. William LeBaron Jenney's home insurance building, completed in 1885, is often considered the first skyscraper because its structural skeleton relied heavily on steel and iron framing rather than thick masonry walls. The building itself was modest by later standards, but its implications terrified and inspired the construction world simultaneously. A city no longer needed to spread endlessly outward. It could rise. Soon New York joined the race. Manhattan possessed one overwhelming advantage and one overwhelming curse. Its granite bedrock provided excellent support for tall buildings. But the island's geography trapped expansion between rivers. As immigration and finance intensified, land prices reached absurd levels. Developers discovered that every additional floor multiplied profit. Height became economics converted into steel. The Skyline turned competitive. Newspapers treated skyscraper announcements like declarations of war. The New York World Building, the Park Row Building, the Singer Building, the Metropolitan Life Tower, and eventually the Woolworth Building, each attempted to surpass previous limits of height and engineering spectacle. But the higher these structures climbed, the more primitive existing construction methods appeared. Traditional cranes lacked sufficient lifting capacity. Manual riveting slowed projects catastrophically. Wind movement across partially completed frames created alignment problems severe enough to halt work entirely. Construction sites expanded into tangled forests of temporary scaffolding, steam pipes, pulley systems, boilers, and unstable lifting rigs. Every additional story magnified risk exponentially. Developers responded the only way industrial America understood, by increasing mechanical force. The machines evolved in stages. Early steam cranes adapted railroad engineering principles into urban construction. Derrick systems mounted atop unfinished towers lifted beams vertically through narrow spaces impossible for conventional equipment. Pneumatic riveting systems accelerated assembly while reducing some manual strain, though they introduced deafening noise and dangerous vibration. Steam-powered compressors fed entire networks of industrial tools simultaneously. By the turn of the 20th century, skyscraper construction resembled military logistics more than traditional building. Entire rail cars of steel arrived daily from Pennsylvania mills. Temporary machine shops operated inside construction zones, repairing damaged equipment around the clock. Boiler crews maintained steam pressure continuously because a loss of pressure could halt operations across multiple floors simultaneously. Then came the giant compression systems. These massive integrated structural machines were designed not simply to transport steel, but to force it into alignment under extraordinary pressure. Engineers borrowed heavily from shipbuilding, railroad bridge construction, and industrial forging technology. Hydraulic jacks capable of exerting hundreds of tons of force corrected warped columns. Traveling gantry systems moved along unfinished frames, carrying lifting equipment directly into the sky. Multi-ton riveting hammers synchronized entire assembly crews into mechanical rhythm. The 14,000-ton steel Colossus was not a single-named machine hidden in one factory. It was the collective industrial organism created when all these systems merged together across America's skyscraper boom. By the 1910s and 1920s, major urban construction projects effectively became temporary mechanized empires. Some construction sites consumed more electricity than nearby neighborhoods. Some required dedicated rail sidings solely for steel delivery. Some operated 24 hours a day beneath floodlights, while steam drifted across the skyline like battlefield smoke. And behind all of it stood the companies profiting from the vertical transformation of America. Bethlehem Steel became one of the most influential forces in skyscraper construction. Originally founded in Pennsylvania during the 19th century, the company expanded aggressively into structural steel production. Bethlehem supplied steel for bridges, railroads, warships, and eventually many of the nation's most iconic skyscrapers. Its factories operated at enormous scale, feeding urban growth with relentless consistency. U.S. Steel, formed in 1901 through the consolidation of Carnegie Steel and other major firms under financier J.P. Morgan, became the first billion-dollar corporation in American history. The sheer scale of the company reflected the nation's industrial appetite. It controlled mines, railroads, shipping fleets, mills, and fabrication plants in vertically integrated systems designed to dominate steel production entirely. The skyscraper was no longer architecture. It was industrial conquest. Cities demanded these colossal structures because modern capitalism required concentration. Insurance companies needed vast office floors filled with clerks processing endless paperwork. Financial firms needed centralized trading operations connected by telegraph and telephone systems. Railroads needed terminals capable of managing unprecedented passenger volume. Corporations wanted headquarters that physically embodied economic power. Height became propaganda. A taller building signaled dominance to investors, competitors, and the public alike. But these towers also solved practical crises created by industrial urbanization itself. Elevated office density reduced commuting distances within crowded city centers. Steel frame construction improved fire resistance compared to older timber-heavy methods. Centralized skyscrapers concentrated utilities, communication systems, and labor into more manageable forms. The machine was dangerous because the city had become impossible without it. Nowhere was this clearer than during the construction booms of the 1920s. America entered a period of extraordinary economic optimism after World War I. Industrial output surged. Stock markets expanded rapidly. Urban populations exploded further. Architects envisioned towers no longer measured merely by practicality, but by symbolic supremacy. The Chrysler Building and Empire State Building emerged from this atmosphere of competitive gigantism. Constructing such towers required industrial coordination on nearly military scale. Thousands of workers moved through sites governed by machine precision. Steel arrived according to exact schedules because storage space in Manhattan barely existed. Riveting crews worked at astonishing speed, sometimes securing hundreds of rivets per shift while balancing hundreds of feet above traffic. Cranes climbed the structures they were helping create, disassembling and reassembling themselves higher as construction progressed. The machine systems themselves grew increasingly immense. Temporary derricks capable of lifting dozens of tons swung over crowded streets. Compressors thundered continuously through the workday. Riveting hammers generated impact strong enough to vibrate nearby buildings. Construction elevators carried workers upward through skeletal shafts open to freezing wind and rain. At street level, pedestrians watched steel emerge upward with almost supernatural speed. Entire floors appeared within days. Newspapers celebrated the efficiency while rarely documenting the injuries occurring overhead. Yet beneath the triumphalism, fear remained constant. Many engineers privately worried skyscrapers were advancing faster than safety understanding allowed. Wind stress calculations remained imperfect. foundation engineering continued evolving under real-world pressure. Construction fatalities were common enough to become normalized within the industry. But economic incentives overwhelmed caution. Every successful skyscraper increased pressure for another. Cities outside New York and Chicago soon joined the movement. Detroit, Cleveland, Philadelphia, and St. Louis embraced steel frame expansion as symbols of industrial modernity. Banks financed taller buildings because visible scale reassured investors. Governments encouraged infrastructure expansion around growing urban centers. Insurance firms adjusted policies to accommodate vertical construction despite mounting risks. The machine spread because the entire nation reorganized itself around its existence. Even the labor system adapted accordingly. A new class of industrial workers emerged specializing in high steel construction. Many came from immigrant communities accustomed to dangerous labor. Mohawk ironworkers became especially renowned for their willingness to work at extreme heights, earning reputations for fearlessness while navigating narrow beams hundreds of feet above city streets. Construction camps, boarding houses, saloons, and union halls formed social ecosystems around the skyscraper industry. Workers traveled from project to project, following demand across expanding cities. Injury, alcoholism, and economic instability became common features of this labor culture. Yet despite the danger, many workers pursued the industry because the wages exceeded those available in factories or docks. The machine consumed bodies, but it also fed families. That contradiction became central to America's industrial identity itself. By the early 20th century, the steel colossus had become more than a construction system. It was a national philosophy transformed into mechanical form. Its towering structures represented confidence, wealth, industrial power, and technological supremacy. Its machinery represented force elevated above limitation, and its workers stood suspended between admiration and expendability. Building monuments to progress while risking death every hour, the machines remained in motion. The skyscraper began long before the first beam entered the city. It began in fire. Inside the steel mills of Pennsylvania and Ohio, blast furnaces operated continuously, like artificial volcanoes chained to the industrial landscape. Iron ore, coke, and limestone disappeared into towering furnace stacks, while superheated air roared upward through the chambers with hurricane force. Temperatures inside exceeded 3,000 degrees Fahrenheit. Molten iron collected below in glowing reservoirs, bright enough to injure the eyes of workers standing nearby. The sound never stopped. Steam shrieked through pressure lines. Conveyor systems rattled endlessly. Rolling mills hammered steel into shape beneath impacts that shook entire factory floors. Smoke drifted across rivers already poisoned by decades of industrial runoff. From this environment emerged the skeletons of American cities. Structural steel beams traveled eastward by rail in enormous quantities, marked with serial numbers and assembly codes like components of a military operation. By the time they reached Manhattan or Chicago, engineers already knew precisely where each beam would stand inside the future tower. Then the real machine awakened. At street level, skyscraper construction sites resembled mechanized fortresses. Temporary fencing surrounded acres of excavation equipment, steam pipes, compressors, cranes, derricks, boilers, and rail tracks. Coal deliveries arrived constantly because nearly every major system depended on steam power during the early decades of high-rise construction. The foundation came first. Before steel could rise upward, crews had to reach bedrock capable of supporting unimaginable weight. In Manhattan, this often meant excavating through layers of earth, sand, refuse, groundwater, and buried infrastructure beneath crowded streets already vibrating from traffic and rail systems. Steam shovels tore into the ground with brutal efficiency. These machines, some weighing over 80 tons themselves, used giant pivoting booms and steel buckets powered by steam pistons. Operators sat inside cabins filled with heat, smoke, and vibration, while cables snapped tight around enormous gear drums. Each bucket load removed several tons of earth at once. But excavation alone was not enough. Workers descended into compressed air caissons beneath the city to stabilize foundations below groundwater level. Inside these chambers, pressurized air prevented flooding, while men dug through mud and rock in suffocating heat. The pressure itself damaged the body. Workers emerging too quickly risked decompression sickness, known simply as the bends. Blood vessels ruptured, joints locked in agony. Some men became permanently paralyzed. Others died within hours. Above them, the city continued moving. Streetcars rattled overhead while beneath the pavement industrial laborers carved out the foundations of towers that would redefine the skyline entirely. Once the foundation stabilized, the steel assembly phase began. This was where the true Colossus revealed itself. The structural machine was not stationary. It climbed. Temporary derricks rose atop the unfinished steel frame itself. These derricks functioned as towering cranes assembled directly onto the growing skeleton of the building. Steam-powered hoists rotated massive booms capable of lifting steel beams, weighing several tons each hundreds of feet into the air. The derricks constantly evolved upward as construction advanced. Crews dismantled sections of the crane and reassembled them on newly completed floors, effectively forcing the machine to climb its own creation. The motion was relentless. Flatbed rail cars delivered steel to the site continuously. Steam winches pulled beams from street level upward through narrow openings between columns. Hookmen guided swinging loads manually using ropes while balancing on exposed girders only inches wide. Wind transformed everything into danger. At 200 feet above the street, steel beams already swayed perceptibly. At 500 feet, gusts became violent enough to swing suspended loads unpredictably through open air. Workers compensated through instinct and experience rather than formal safety systems. Then came alignment. Even tiny imperfections in steel positioning created enormous problems across tall structures. A beam misaligned by fractions of an inch at one level could distort entire sections above it. Temperature changes caused steel expansion and contraction throughout the workday. Sunlight heated one side of the structure, while shaded sections remained cooler, subtly twisting the frame itself. The machines designed to correct these distortions were brutal instruments of force. Hydraulic jacks pressed beams into alignment using hundreds of tons of pressure. Chainfalls tightened steel members together, while crews hammered drift pins through partially aligned rivet holes. Giant screw mechanisms slowly compressed warped sections into position. The noise became unbearable. Pneumatic riveting hammers operated through compressed air generated by enormous steam-driven compressors below. Flexible hoses snaked upward through the structure, carrying high-pressure air to riveting crews working across multiple floors simultaneously. A single riveting gang usually consisted of 4 men. The heater worked beside a portable forge where rivets glowed orange-white inside coal-fired furnaces. Using long tongs, he removed each heated rivet and tossed it through open air toward the catcher. Sometimes the throw traveled over 30 feet across exposed beams suspended hundreds of feet above the streets. The catcher trapped the rivet in a metal bucket or glove before inserting it rapidly into pre-drilled holes connecting steel members. Then the gunman activated the pneumatic hammer. The machine exploded into motion instantly. Rapid impacts slammed the glowing rivet repeatedly until the softened metal deformed and locked permanently into place. A second worker held a heavy bucking bar against the opposite side to absorb force and shape the rivet head correctly. Sparks burst outward. The steel rang like a struck bell. Entire floors vibrated with each impact. A large skyscraper required millions of rivets. The rhythm became mechanical warfare against steel itself. Crews developed hand signals because verbal communication disappeared beneath the constant roar of compressors, hammers, steam vents, and moving machinery. Some workers eventually suffered permanent hearing damage after years inside these environments. And all around them, the city climbed upward. Temporary elevators carried materials and workers through open shafts lined with unfinished steel. These hoists operated through steam engines or electric motors connected to winding drums below. The cables themselves remained a constant source of terror. A snapped hoist cable could send entire platforms crashing downward through the skeletal building. Many did. Construction platforms hung from cables attached to derricks above. Workers standing on these narrow wooden decks handled tools, rivets, and steel components, while exposed to open air on all sides. There were few guardrails. Safety harnesses remained rare during the early decades of skyscraper construction. The machine valued momentum over protection. At night, floodlights illuminated the structures against smoke-filled skies, while crews continued working around the clock during critical phases. Steam drifted upward through the beams like fog. Riveting sparks cascaded downward through darkness toward the streets below. Pedestrians stopped to watch because the process appeared almost supernatural. Steel towers emerged from the earth with astonishing speed. But inside the machine, every sensory detail carried threat. The smell was a mixture of coal smoke, hot oil, sweat, ozone, wet timber, and heated steel. The vibration traveled through boots, knees, and spine continuously. The air changed with altitude. Higher floors became colder, windier, and more unstable. Workers learned to read machinery instinctively. The sound of a stressed cable, the vibration of an overloaded derrick, the change in steam pressure inside pneumatic lines, the metallic groan preceding structural movement. Mistakes killed quickly. If a suspended beam swung unexpectedly, workers could be knocked directly from the frame. If a rivet failed under pressure, steel joints weakened invisibly. If hydraulic systems slipped during alignment, entire sections shifted violently. Some accidents became legendary within the industry. Dropped tools fell hundreds of feet with enough force to penetrate pavement. Crane collapses twisted steel structures into wreckage. Boiler explosions scattered shrapnel across entire construction sites. Partial structural failures trapped workers beneath mangled beams impossible to lift without additional machinery. Yet despite the danger, the machine achieved astonishing efficiency. By the late 1920s, some skyscrapers rose at nearly unbelievable speeds. During construction of the Empire State Building, crews averaged approximately 4.5 stories per week at peak progress. More than 57,000 tons of steel assembled into place through synchronized industrial coordination. The machine functioned because every component depended on every other. Steel mills supplied standardized beams. Railroads delivered materials precisely. Cranes lifted. Compressors powered riveting systems. Boilers maintained steam pressure. Hydraulic systems corrected alignment. Workers adapted their bodies to the rhythm of industrial force. Even weather became part of the calculation. Rain slowed riveting. Extreme cold altered steel behavior. Wind speeds determined lifting operations. Fog reduced visibility across high steel. The skyscraper was not constructed by human labor alone. It was manufactured through a temporary industrial ecosystem as complex as the city it intended to create. And at the center of that ecosystem stood the steel Colossus itself. Not a single machine, but an integrated mechanical civilization devoted entirely to vertical expansion. 14,000 tons of moving force, steam, pressure, heat, cable tension, steel impact, human coordination, all synchronized toward one purpose: to overpower gravity long enough for the modern city to rise into the sky. The photographs rarely showed the fear. They showed men smiling on steel beams hundreds of feet above Manhattan, lunch pails balanced beside them, cigarettes hanging loosely from their mouths, boots dangling over empty air while the unfinished city stretched beneath them in geometric shadows. The images became symbols of industrial courage. But the photographs never captured the trembling afterward. They never captured the worker lying awake at night, hearing phantom hammer strikes echo inside damaged ears. They never showed the swollen hands, the ruptured joints, the coughing fits blackened with soot and metal dust. They never showed the widows waiting beside apartment windows long after midnight, because construction delays often meant somebody had fallen. The machine made fear ordinary. You woke before dawn in a boarding house, already filled with exhausted breathing and the smell of wet work clothes drying beside radiators. You walked through streets darkened by coal smoke toward a construction site where the steel frame disappeared upward into fog. Steam drifted between the girders. Compressors were already running before sunrise. The noise reached your chest before your ears. Pneumatic hammers rattled through the structure continuously. Boilers hissed beneath pressure. Derrick engines rotated overhead while steel beams swung across open air like suspended battering rams. And then you climbed, sometimes 20 stories, sometimes 60, sometimes higher than any human being in your family had ever stood above the earth. There were no real safety systems in the early decades, no secure harnesses, no shock-absorbing cables, no modern hard hats during the earliest years of skyscraper expansion. A worker balanced on narrow steel beams, often less than a foot wide, while carrying tools, rivets, or alignment pins through wind strong enough to shift his center of gravity unexpectedly. One slip was enough. The falls became so common that newspapers often reduced them to short paragraphs buried beneath larger headlines about economic growth and engineering achievement. Steelworker killed in fall. Riveter dies on Uptown Tower. Construction accident delays project. The city learned to absorb these deaths mechanically, almost without reflection. By the early 20th century, industrial labor fatalities had become woven into the economics of progress itself. On some skyscraper projects, workers died so frequently that crews developed superstitions around specific floors or sections of the structure. Men spoke quietly about unstable beams, unreliable derricks, or cursed elevator shafts. Some refused to work certain positions after previous accidents. Others drank heavily before shifts simply to quiet the terror long enough to climb. Alcohol moved through the construction world like medicine. So did silence, because fear carried consequences. A worker who hesitated too often might be replaced. A man injured badly enough to miss work could lose his place entirely. There were always more laborers arriving from immigrant neighborhoods, railroad camps, mining towns, or failed farms searching for wages inside the expanding industrial cities. The machine depended on replaceability, and the bodily strain extended far beyond the risk of falling. Riveters suffered permanent nerve damage from vibration exposure after years operating pneumatic guns powerful enough to shake the bones inside the arm itself. Hearing loss became almost universal among long-term steelworkers because compressors and riveting hammers created continuous industrial noise levels capable of damaging hearing within minutes by modern standards. Many workers developed respiratory illnesses from constant exposure to coal smoke, asbestos insulation, welding fumes, dust, and chemical coatings used on structural steel. Others endured what the workers themselves called the shakes. After long shifts balancing above open air while absorbing constant machine vibration, their muscles continued trembling even after returning home. Some men could no longer hold utensils steadily during meals. Some woke suddenly at night convinced they were falling. And then there were the crush injuries. The steel Colossus operated through momentum. A swinging beam weighing several tons could kill instantly. Cables under extreme tension snapped violently enough to sever limbs. Hydraulic systems failed without warning. Derrick collapses transformed entire sections of unfinished buildings into twisted wreckage within seconds. One of the most feared dangers involved structural shifting during alignment operations. Steel did not always behave predictably under pressure. Temperature fluctuations caused expansion and contraction across enormous frameworks. Miscalculations could release stored force suddenly through the structure itself. Workers caught between moving steel rarely survived intact. Hands disappeared first, then feet. Then entire bodies vanished beneath collapsing sections impossible to lift quickly enough. In many cases, recovery operations themselves became additional industrial disasters. The machine consumed rescuers alongside victims. During the skyscraper boom of the 1920s and early 1930s, construction speed intensified every danger further. Developers demanded impossible schedules while competing for symbolic dominance through height itself. The Chrysler Building and Empire State Building became public spectacles of engineering speed, each racing against economic deadlines and public expectation. Crews worked through winter storms, exhaustion, and dangerous wind conditions because stopping construction cost enormous sums daily. The Empire State Building officially recorded only a handful of deaths during construction, though historians continue debating the true number because many injuries and indirect fatalities disappeared within subcontracting systems or went underreported entirely. Even when workers survived accidents, their bodies often did not survive the industry. Aging steelworkers carried lifelong injuries, damaged knees from climbing unstable frameworks, arthritic hands warped by vibration and cold, respiratory damage from industrial dust, chronic pain from repetitive strain and impact exposure. Many died younger than wealthier urban residents benefiting from the very skylines they helped construct. That contradiction haunted the industrial city itself. The towers symbolized prosperity. The labor beneath them often resembled controlled sacrifice, and eventually, the machine began destroying the environment surrounding it as thoroughly as it damaged the workers operating within it. Steel production poisoned rivers with chemical runoff. Coal combustion darkened urban skies beneath permanent smog. Construction debris buried waterfronts and wetlands. Entire neighborhoods disappeared beneath expanding business districts engineered for corporate growth rather than human stability. The skyscraper reorganized the American city economically and physically. Working-class communities were pushed outward, while financial districts concentrated wealth vertically into monumental steel towers. Elevators separated executives from laborers not only by floor, but by entire social realities. At the top existed climate-controlled offices overlooking the city. At the bottom existed boiler rooms, freight elevators, machine spaces, and maintenance corridors where industrial labor remained invisible. Yet despite the suffering, the machine succeeded. That was the most unsettling truth of all. The steel Colossus worked. It transformed New York into a vertical capital of global finance. It allowed Chicago to rebuild itself after catastrophe. It enabled urban density impossible under older construction methods. It created the modern skyline, now associated with American power itself. The Empire State Building, the Chrysler Building, the Woolworth Building, Rockefeller Center. These structures became monuments not merely to architecture, but to industrial coordination on unprecedented scale. And because the machine succeeded, it spread everywhere. Cities across the world adopted steel frame construction and mechanized high-rise assembly. Construction equipment evolved rapidly after World War II. Diesel engines replaced many steam systems. Electric cranes grew vastly more powerful. Welding reduced dependence on rivets. Safety regulations slowly emerged after decades of labor activism and public pressure. The old machine began disappearing. Steam derricks vanished from skylines. Coal-fired compressors fell silent. Pneumatic riveting gangs gave way to welding crews and bolted steel systems. Hydraulic cranes replaced climbing derricks. Modern harnesses, helmets, and regulations reduced, though never eliminated, construction fatalities. The steel Colossus evolved into cleaner, faster, more efficient descendants. But traces of the old machine remain embedded everywhere inside the modern city. Deep beneath Manhattan, foundation caissons still support towers raised during the first skyscraper age. Riveted steel skeletons remain hidden behind stone and glass facades. Old construction photographs survive, showing workers suspended above unfinished streets, while clouds drift below them. And some of the original steel still carries the marks: hammer scars, rivet distortions, alignment stress, physical evidence of a period when human bodies and industrial machinery fused together in order to force cities into the sky. Today, tourists stand atop observation decks, taking photographs of skylines once considered impossible. Office workers ride elevators through structures assembled by men who balanced on naked beams without protection. Millions inhabit cities shaped permanently by machines most people no longer remember. But the machine is still there, not physically in its original form, but structurally, psychologically, economically. The modern city still depends on the same industrial bargain first accepted during the skyscraper age. That progress requires force, that scale requires sacrifice, that every monument to civilization hides an invisible architecture of labor beneath it. And somewhere inside the steel bones of America's skyline, the echoes still remain. The hammer strikes, the steam whistles, the cables tightening, the roar of 14,000 tons of machinery forcing steel into place while men stood beneath it, knowing the city would continue rising whether they survived or not.